Hello everyone, welcome back. This is 3.1, a discussion on quadratic functions and models. I'm not going to talk too much about models. Models, by the way, are just functions that represent certain applications of everyday life sort of problems. We'll take a look at, I think, one example in this lecture, but aside from that, I want to mainly focus on what a quadratic function is and certain properties of it. So let me start off by saying a quadratic function is a function of the form f of x equals some quadratic polynomial ax squared plus bx plus c, where of course, let me say a is not equal to 0. It's possible b and c are 0, but a not 0. If a was 0, then it's linear and not quadratic if you kind of cover that up. And now let me go on to say that the graph of any quadratic function is a vertical parabola. Much like the graph of any linear function is a line, well, here we'll have a parabola. Now it's a vertical parabola. There do exist sideways parabolas or even slanted parabolas, but you can figure that out for yourself. Those wouldn't be functions because they would fail the vertical line test. Only a vertical parabola does not fail the vertical line test. Okay. Now, parabolas have certain properties that I want to talk about. There are certain items that we need to list out. The first is the vertex. And the vertex is either the max or min of the parabola. Here in the case where it opens up, it has a minimum, so I'll label that as V for vertex. And here in the case where the parabola opens down, it has a maximum point, and I'll label that again as V for vertex. The next thing is that we have this axis of symmetry. So axis of symmetry will always have this vertical line that passes through the vertex. And I'll always label this as AOS, standing of course for axis of symmetry. So there's one here and one here for each parabola. The next thing is, of course, I spoke about this already, either it opens up or it opens down. So the parabola can open up or down, not both. We'll discuss more on this in the next screen. And then finally, as far as x and y intercepts are concerned, a parabola will always have a y-intercept. As it opens up or opens down, it indefinitely spreads as well. So it gets further and further away from it. It doesn't go straight down or straight up only. It doesn't have vertical asymptotes, basically. It just spreads open indefinitely in each direction. So there always exists a y-intercept. X-intercepts, not so much. And it kind of depends. And let me try to give you this idea here. So imagine for a moment that this is the x-axis. If this was the x-axis, well, notice that it doesn't pass through this parabola at all, so this parabola would have 0 x-intercepts. But for the downward case, it actually passes through it twice if you extend this further. So that's why I say it has at most 2 intercepts. Is it possible to have 1 intercept? Certainly it is. If you imagine I shifted this x-axis up a little bit so that it passed through the vertex, that would pass through it once. So to have 1 x-intercept would be when the x-axis passes through the vertex of the parabola only. And now we'll take a look at a little bit more information regarding these items. Alright, so now let me say that the graph of f of x equals ax squared plus bx plus c, any quadratic function, has the following properties. So the parabola, it's always a parabola, we said that earlier. So the parabola will either open up or down. It opens up, actually, when the leading coefficient, a, is bigger than 0, and open down when a is less than 0. And remember, a is never 0, or else it wouldn't be a quadratic function. Okay, the vertex of the parabola would be labeled V for vertex, and we label this as h comma k, where f of x is equal to a times the quantity ax minus h all squared plus k. This is what is known as vertex form. And by the way, this way of writing a quadratic function is known as standard form, opposed to vertex form. And after I finish discussing these, in the next screen I'm going to explain how you can translate between the two. And as it turns out, me labeling this as A is no coincidence that this is the same A actually. So the A value here is actually the same, but now it's just how do you get from A, B, and C to H and K, and we'll discuss that after this. But let me go on to say now the axis of symmetry, moving on with this discussion of these items. The axis of symmetry is always going to be x equals h. Always. Because what we saw earlier, it's a vertical line that passes through the vertex. So if it passes through the vertex, then its x value is the same as that of the vertex. It's just the x value of the vertex. H is the x value of the vertex. Why it's the line x equals is because x equals a number is a vertical line. If you recall, y equals a number would be a horizontal line, so that's why it has this equation. And then the y and x intercepts are just what you think they would be. To find y-intercepts, you said x equal to 0, so they're of the form 0, comma f of 0. And to find x-intercepts, you just set f of x equal to 0, and then you write x, comma 0. So those x values, comma 0. And now we'll see the relationship now between vertex form and standard form of any quadratic function. Okay, so there's a really nice way to find out what h and k are in terms of a, b, and c. But before I move on, let me just say the following. Any quadratic function can be written in vertex form. How do we know this? Well, it's because we already agreed that every quadratic function has a graph that is a parabola, okay? Now, if you consider the parabola y equals x squared, let's just think of this for a second as a parent function. And we saw from chapter 2 that we can apply transformations to make this look actually like any parabola. How? Well, if you do minus something on the inside, that'll give you horizontal shifting of the parabola. If you add a number on the outside, that'll give you vertical shifting of the parabola. And then if you multiply it by a number on the outside, that'll stretch it or widen it accordingly. At the same time, if a is negative, it'll flip it across the x-axis. So if you imagine doing these things to x squared, then to get a new function f of x, this will actually be any parabola you want it to be. Meaning, any equation that has a parabola, any function that has a parabola as its graph, like this quadratic function, can be written as a transformation of just x squared. So now, to find h and k, here's what we're going to do. I'm going to suppose that they're equal. We already agree, based on that conversation I just had with you, that they are indeed equal. You can write any quadratic function in this vertex form. We're going to expand this out, and then we're going to set things equal to each other. Because remember, a, b, and c are just numbers. A, h, and k are just numbers. X is the only variable. So let's see. If we expand this out, we get x squared minus 2xh plus h squared, and then plus k. If you distribute this a, you get ax squared minus 2a, let me write it like this, 2ah times x, plus ah squared, and then plus k. Now there are a lot of things that we're learning from this. So notice, this is ax squared, this times x, and then this. So what I'm trying to emphasize on is that we're going to do what is called equating coefficients. So the coefficients of ax squared, x, and the constant term will be exactly what they are here if these are indeed equal expressions. So a is going to be equal to a, no news there. So we didn't learn anything as far as that goes. B is going to be equal to negative 2ah, so that's something new. And then C is going to be equal to this quantity, ah squared plus k. I'm not really going to worry about the last one so much. What I am going to worry about, though, is the middle two. So B is equal to negative 2ah. Let's write that. B is equal to negative 2ah. And what are we trying to do? We're trying to solve for h and k. So if you divide by negative 2a, you get that h is equal to negative b over 2a. And this is how we're going to find the x value, h, of the vertex in terms of a and b. Notice we don't even need c. Now, how do we find k? Well, notice if you set this equal to c and then solve for k, you can find an equation for k. But I'm not going to worry about that. And the reason why I'm not going to worry about that is because of the following. Any point on a parabola, just for instance, let's say it's an upward parabola, but it doesn't matter, it could be downward. This parabola is the graph of the function f, let's say, and this is the point v, which is h, comma, k. So just imagine for a second that the layout's like this. Doesn't really matter, but the point is the following. If here the x value of the point is h, then of course the y value of this point will be k, but more importantly, since it is the point on this function f, then k has to be f of the x value. And that's something we learned when we discussed functions. The graph of any function has points that satisfy that. The x value comma f of that x value. Plugging that x value into the function will give you the y value. Meaning, if h is negative b over 2a, then we know exactly what k is. K is just f of negative b over 2a. Now we're going to take a look at examples of finding the vertex, and we can go beyond this and actually find all of the items we just discussed in a previous screen, and then finally sketch a graph of a parabola. So let's see that right now. Alright, so for this example, I'm not being specific as far as what the instruction is, but what I want to do basically is get to the point where I can sketch a graph of the function. But first off, what I want to do is I want to discuss, well, what those items we saw earlier were. So notice here, before we get started, a is 1, b is negative 6, and c is 2. This is in what we call standard form, and we can now find the vertex by finding the individual pieces. H, as we just saw, is negative b over 2a, so that's negative 6, because b is negative 6, over 2 times 1, because a is 1. Double negative is positive, 6 over 2 is 3, so h is just 3. Let me just write that here to feel a little more complete about things. Now that we have h is 3, can we find k? Yes, it's just f of h, like we saw earlier. Since h is 3, k is f of that. So let me just say specifically, we're using the fact that k is always f of h. Since we found out what h was first, we can plug it into f now to find what k is. So plugging in 3 into this expression, we get 3 squared minus 6 times 3 plus 2. So that's 9 minus 18 plus 2. If you do the positives first, 9 plus 2 is 11, and 11 minus 18 is negative 7. So I'm getting negative 7. So altogether here, k is negative 7. So the vertex actually is then the point h comma k, so 3 comma negative 7 for the vertex. The next thing I want to do is I want to see if we can write this in vertex form. Let me just write it to show you. So vertex form is f of x equals a, which is just 1, times x minus h, which is 3 squared, plus negative 7, I'll just write minus 7. So this is vertex form of the function here given the vertex. Now, of course, that's why I call it vertex form, but I want to be a little clearer here. The book we're using doesn't call it vertex form, it calls it standard form. Now that sounds really confusing because I call this standard form, but you'll just have to make do with that. So in the exercises when they ask you to convert it to standard form, they really mean convert to vertex form. So as long as we have that vocabulary out of the way, that's fine. But I think it should be called vertex form. In fact, this is the only book I've seen that makes that a distinction in the vocabulary for some reason. I understand their point because this should be the standard we're aiming for. But normally we see this, and as a consequence, this would have to be named something else. And what I name it as is after the vertex because we're using this specifically to find the vertex. But anyways, it's kind of a formality, I guess. Alright, so now what is the axis of symmetry? Remember, the axis of symmetry is always the line x equals the x value of the vertex, which is 3. So that's the axis of symmetry. And I'm going to erase this and we're going to find the x and y intercepts, and finally we're going to graph. Alright, so I filled out some things here as far as what we just found versus what we want to find now. Now the y-intercept is just going to be the point 0, comma, whatever you get when you plug in x equals 0. So let's see, f of 0 is 0 squared minus 6 times 0 plus 2. It's really just 2. And in fact, always it is the case that the y-intercept is always 0, comma c, which I guess I could have said in the previous section where we discussed the y-intercept, but you know that's fine. Just plug in 0, you'll always get c though. So 0, comma 2 is a y-intercept. The x-intercept is tricky in this case, and here's why. Well, remember that a is 1, b is negative 6, and c is 2. So now, if we use, writing this equals 0 to find the x-intercept, to solve this equation, this is actually not factorable. You can try to factor it, but it's not doable. Instead, we kind of have to use here, actually, is quadratic formula. So let's see if we can apply quadratic formula. So applying quadratic formula with these values of a, b, and c will give us what? Let's see. So we'll get x is equal to negative b, which is positive 6. Right? Negative 6 is positive 6. We saw that already. Plus or minus the square root of negative 6 squared. So I'm just to be a little quick about things. Negative 6 squared is positive 36. Minus 4 times a times c. And again, to be quick about things, 4 times 1 times 2 is 8. So this is really 36 minus 8. That's all over 2 times a. A is 1. 2 times 1 is just 2. Okay, and finally, what's 36 minus 8? Sorry for the so much erasing here, but I just want to be quick about things so I have more space here. So 36 minus 8 ends up being 28. And radical 28 we can actually simplify because, just to show some work here, 28 is 4 times 7. And though you can't square root 7, you can certainly square root 4. So this is 2 radical 7 because the square root of 4 is 2. So if you split it up, you get 2 times radical 7. So radical 28 is just 2 times radical 7. Okay, now finally, if you divide top and bottom by 2 here, well, you end up getting this. 3 plus or minus radical 7. Because, of course, this is the same as 6 over 2 plus or minus 2 radical 7 over 2. For the first term, we just get 3. For the second, the 2's cancel and we get our radical 7. Okay, so there we are. Now, the problem here, of course, is that these are irrational numbers. We can approximate them, though, and I'm going to do that right now. So all I did here was use my calculator to do 3 plus radical 7, and then secondly, 3 minus radical 7. For the positive case, I got 5.65. For the negative case, I got 0.35. And what I'm going to do now is I'm going to attempt to, well, let's see. The x-intercepts are each of these comma 0, so 5.65 comma 0, and 0.35 comma 0. And I want to talk a little bit about what's going on here. So if you remember from quadratic formula, there are 3 cases. Either the inside of the radical part ended up being 0, positive, or negative. In this case, it's positive, so we have 2 distinct real numbers. When it's negative, you have no real solutions. That would correspond to no x-intercepts for this parabola. So either it's opening up above the x-axis or opening down below the x-axis, meaning it has no x-intercepts. If it was 0 inside the radical, then there'd only be 1 x-intercept, and in that case, the vertex would touch the x-axis, either opening up or opening down. So I'm going to clear this out so we can actually try to plot these things and figure out what the sketch of the graph will look like. The one last thing, though, before we begin to sketch this that I had not emphasized on was, does it open up or open down? Well, it opens up because the number in front of x squared is positive 1, technically. So it opens up opposed to down. But to be quite honest, even if we didn't know this, we could still find that anyways. And here's how we do that. So just so we have an idea of where these things lie, let's make the x-axis go from 0 to 6. 0.35 would be about here, a little less than 0.5. 5.65 is a little more than halfway between 5 and 6, so let's say right here. So these are our x-intercepts. The y-intercept is at y equals 2. So let's say that's right here. Okay. And now what? Well, now if you think about it, the only way we can have a parabola passing through these 3 points is if it looked like this. So that's more or less what the parabola is going to look like. Before I draw the hump part, I want to actually figure out where the vertex is. Now, according to what we found out, it's 3, 7. And it looks like it will more or less be that point. Let's see. So it's 1, 2, 3, 4, 5, 6, and 7. Just to be a little more accurate about things, I'm going to plot that as point V. And connecting them, it seems like it actually lines up, looking like a really nice parabola. Perfect. Now, this is basically what we're going to be doing for these problems in this section. Finding the vertex, changing the function into vertex form, the axis of symmetry. By the way, let me plot that for us. The axis of symmetry is this vertical line here, which is actually a really, really nice thing to know, because what this basically tells us is that if you know any point for any x value on the right side or the left side, then you know the opposite one. So all of these points lie the same distance from each other if they have the same y-intercept. So here, the point 0, 2 from the vertex has a distance of 3, right? So that means if you go 3 in the other direction, you should land at, well, 3 plus 3 is 6, so this should be the point 6, 2, without me even plugging it in. And if you want to check that, yeah, we can plug 6 in. Plugging 6 in gives you 36 minus 6 times 6 is also 36. They cancel and you get 2. Alternatively, you can plug it into vertex form, of course. 6 minus 3 is 3. Squared is 9. 9 minus 7 is 2. 0 minus 3 is negative 3, which is also 9 when you square it. Minus 7 is 2. Perfect. So that's the last thing I wanted to speak of in this example. I'm going to do one more example and then we'll move on finally to an application problem where we can talk about these models I was referring to earlier. Okay, so I want to mention something that we could have done in the last problem that we actually didn't do. Recall we converted to vertex form before we found the x-intercepts. Well, when you do that, you can actually solve for the x-intercepts using vertex form instead of standard form. Meaning you don't have to necessarily use quadratic formula. The square is already completed for vertex form. So essentially we'll use methods of completing the square, but the completing the square part is already done for us actually. So I'm going to try to do that here. First, we need to find the vertex. So here we need at least a and b. Remember, the vertex relies only on a and b for the x value h. So h is negative b over 2 times a. Good. So that's going to be, well, positive 4 over 8, so that's just 1/2. So h is 1/2. Great. Now what's k? K is just f of h. So k in this case is f of 1/2. Good. So now what we have to do is plug 1/2 into this. Well, let's see what happens. So we're going to get f of 1/2 is 4 times 1/2 squared minus 4 times 1/2 plus 21. Now 1/2 squared is 1/4. So it looks a little shaky at first, but actually, after applying some cancellation, we don't get a fraction. 4 times 1/2 is 2. 4 times 1/4 is just 1. So we have 1 minus 2 plus 21. If you add the positives first, you get 22. Minus 2 is 20. So altogether, k is 20. Meaning our vertex is actually just, well, 1/2, 20. Good. And, moreover, the vertex form of the function is the following. It's f of x equals a, which is 4, times x minus h, remember h is 1/2, squared, plus 20. And squeeze it in, perfect. And now let me erase this, and I'll show you how to find the x and y intercepts. I guess before we can do that, we can find the axis of symmetry and the y-intercept. Those are pretty simple to find. The axis of symmetry is always basically setting the inside of this square part equal to 0. It's just x equals the x value of the vertex, as I've been saying. The y-intercept is also super easy. Once you have the standard form, plug in 0, you just get 21. So it's 0, 21. Now all we need to do is find the x-intercepts. And let me erase so we can take a look at that right now. So first off, let me just say, if this vertex form freaks you out for a little bit, you can always expand this out, distribute the 4 combined like terms, and you'll see that you'll get indeed this. So here's how I'm going to find the x-intercepts. I would set this equal to 0, and then we can use quadratic formula that way, but alternatively, let's set this equal to 0 to find the x-intercepts. Notice, isolating the square part, we subtract 20, so we get, after doing that, negative 20 is equal to 4 times x minus 1/2 all squared, and then when you divide by 4, you get this. You get negative 5 is equal to x minus 1/2 quantity squared, and if this doesn't disturb you, well, it should, because this says a square is equal to negative, meaning if you were to square root both sides, you'll get a plus or minus on one side. So let's do the plus or minus on this side, say. These cancel. But then what we get here is a non-real number. We get an imaginary number because you have a negative inside of a radical. Okay, what this tells you is that there are no real solutions. There's no real solutions. Remember how that goes. We saw from 1.5 there are what are called complex solutions, but as far as the graph is concerned, those solutions aren't accounted for when it comes to the graph. So with that being said, no real solutions mean there's actually no x-intercept. Funny. So there aren't any. Let me just say D and E for does not exist. But I'm going to put a sad face because that makes me kind of sad. In reality, I shouldn't be sad. I should be kind of happy because it should make this all easier to graph. And in the space we have, I believe we can do that. Let's see. I want to make sure I have the right... I guess it's okay. Let's just make it like this, let's say. Now, first off, the vertex is 1/2, 20. So let me just say this is not to scale. But we're going to have, let's say, 20s here. And let's say this is 1/2. Then this would be the vertex. Is that okay? 1/2, 20. The y-intercept is 21, which is a little bit above 20. Let's say it's there. Again, this is not to scale. We only have 2 points now opposed to the 3 we had from the previous example, but we know this is a facing up parabola because a is positive. Also, if it were negative, well, if the parabola were facing down, then we would have x-intercepts. But since the vertex is here, above the x-axis, and we found that there are no x-intercepts, it has to face up. In fact, if you wanted to find one more point, you can actually translate across the axis of symmetry. The distance here is 1/2, so if you move 1/2 away from the vertex, you arrive at 1, and 1 should also correspond to the y-intercepted value, 21. And you can see that by plugging 1 in. Notice here the 4's cancel. When you plug in 1, you just get 21. So that's all I'm going to say about the graph there. But this is what it could possibly look like if you have no x-intercepts. And from this, we also learned there is an even, maybe not better, but there's a different way of finding the x-intercepts taking advantage of vertex form. Crazy. Now, finally, we're going to do the application problem I was talking about. We'll see that right now. Alright, so this is the problem I wanted to take a look at. A farmer wants to fence off an area that borders a river. See diagram below. We'll talk about the diagram in a second. If the area is to be rectangular and the farmer only has 1,200 feet of fencing, what is the largest such area? Well, let's see. So looking at the diagram, it looks like we're not bordering the part that borders the river. That's not in the sentence, but it says to look at the diagram, and that's what it tells me. Also, we only have 1,200 feet of fencing, and we want to use all of it, which is also not said, but you know the wording's a little fishy anyways. So what we're kind of assuming here actually is that all of these three sides will add up to a total of 1,200. Good. The next thing is it's rectangular, meaning this length will be equal to this length, right? If we call each of these lengths x, I guess you could call this remaining length y, but let me just tell you, if you call it y, well notice x plus y plus x is just what? Well, of course, x is combined to 2x, so this is really 2x plus y. But more importantly, it's equal to the total amount of fencing we're using, which is 1,200. So actually, you can solve for y by subtracting 2x. So really, we shouldn't call it y, we should just say it's the total minus 2x. Once we have these labelings, well, what do we want to find? We want to find the largest such area. So we want to find area. So what we can do is we can find the area by, well, what's the area of a rectangle? It's length times width. So the area as a function of x, because x can possibly change, will be the length times width. So it's going to be 1,200 minus 2x all times x. And notice, after expanding this out, well, let me write it a little differently. In order, it's going to be negative 2x squared plus 1,200x. And what you may notice about this function of x is that it's a quadratic function, meaning its graph is a parabola. And it's a facing down parabola because the leading coefficient is negative, meaning the facing down parabola, let's say it looks something like this, has a maximum. And what is its maximum? It's just the vertex. So to find the largest such area, all we need to do is find the vertex of the parabola. Now the x value will be what x is, but the y value will correspond to what a of x is, which is the area. So once we find the y value of the vertex, we're done. So let's see. To find the vertex, we need to find h, which remember how that goes. It's negative b over 2a. So negative 1200 over 2 times a. A is negative 2. There's no c in this case. C is 0, so that's fine. We end up getting 1200 over 4, so that's 300. Of course, 2 times negative 2 is negative 4, but the negative over negative is positive, so I'm ignoring that. And I'm ignoring the negative part. So there's h, and now we got to find k. I ran out of space here, so I'm going to erase this, clean this up, and we'll find k. K is the y value of the vertex, so we'll be done. So let's see that right now. Alright, good. So this is h, so this is our function, so let's find k. Remember, k is just the function evaluated at the h value, the x value of the vertex. So plugging 300 into this, I guess we can do it like that. I wanted to do it maybe like this better. In fact, maybe it's better if we do it like that because it's just the area. So what we found out then is that we want x to be 300. And if x is 300, then what is y? Well, it would be this value, not this y value, but this, what we called y earlier. The length is 1200 minus 2 times 300. 2 times 300 is 600. 1200 minus 600 is just 600. So actually, a of 300 will be 6 times 8, which is 18, with 2 zeros. And it's going to be in feet squared because the area will be in feet squared if each of the lengths are in feet. Now, of course, you may have not expected me to do it that way. So that's a total of 180,000 square feet. But you can check for yourself. If you plug 300 into this expression, you'll get this indeed. In fact, I don't want to leave you hanging. I'll just do it for you, I suppose. So if you plug 300 into this, you get negative 2 times 300 squared plus 12 times 300, 1200 times 300. So notice this is going to be negative 2 times 3 squared is 9. 300 squared is 9 with 4 zeros because you double the amount of zeros you have when you square. Here, this is going to be 3 times 12, which is 3600, or 36, with 4 zeros is what I meant to say. Good. Negative 2 times 8, negative 2 times 9 is negative 18. Again, we have 4 zeros. Plus 36 with 4 zeros. So really, they have the same amount of zeros, so this is just 36 minus 18 with 4 zeros. Which is exactly what I said it would be, just doing it a different way. And yeah, that was the application I wanted to show you. This, by the way, is the model I was talking about. This is a particular example of a function that models a, well, I guess a certain attribute in real life problems. In this case, it's area. But you could have a model for different things like population growth, let's say finance as far as like cost or profit go. But I only wanted to do one example of this. You won't really see this too much in the homework or anything. But there we go. There was one example of that. Thanks for watching. I hope you really enjoyed this. And I'll see you in the next video for 3.2 and the rest of chapter 3. See you then.